Hello everyone. In this video, we are going to talk about the Fleming's left hand rule and the Fleming's right hand rule. And we'll see whether these two rules are really necessary or we can do away with them. So I have two situations which are depicted on the board. Here in the first situation, you can see that I have made many crosses on the board. These crosses are equidistant and they are representing a uniform magnetic field which is directed inside the plane of the board. And here I have this metallic frame. This is the metallic frame which is rigid, and I have attached to this frame a battery, and this is the key. Now I will put a wire on this frame. This wire, I'll name it as AB from here to here. This wire can slide over this metallic frame. Now, when I close this key, then what will happen? A current will start flowing in this loop. So, we'll close this key. And the direction of the current, you can see from positive to, it will go like this and this. So this is the current which will flow in this circuit. Now, I have this current carrying wire which is straight and it is kept in a magnetic field. So, it will experience a force. This force is given by equation F is equal to I L cross B. B here is the magnetic field. L is the length of this wire, but I have put a vector sign on it. That is because I have given it a direction, and this direction is the direction of the current. So the L vector has a direction which is along the direction of the current. Now, according to the Fleming's left hand rule, we can find out the direction of the force on this wire. For that, we'll use our left hand. So this is my left hand and I have, you see, oriented my three fingers mutually perpendicular to each other. So which fingers are they? This is the middle finger, this is my forefinger, and this is the thumb. The forefinger will represent the direction of the magnetic field. The middle finger, so this finger, middle finger, will represent the current, and the thumb will give me the direction of the force. So let us find out what is the direction of the force. I will orient my forefinger inside the plane of the board. So inside is the magnetic field, that is how my forefinger is pointing. And this is the direction of the current in the wire AB. So the force on this wire will be in this direction. You can see the thumb is pointing in this direction. So the wire, because it can slide, it will move towards this side. Okay, so it will cause a motion of the wire towards this side. Now, what about the Fleming's right hand rule? For that, I have another situation. Again, I have put these crosses which represent a uniform magnetic field, again directed inwards. And we have this metallic frame, you can see, but now there is a difference. There is no battery attached to this frame. I am again going to put a wire over this and call it AB. Now, this time I will move this wire over this frame. So, if I slide this wire in this direction, so if this is the direction of motion, let's say it's moving with a velocity v and the magnetic field is inside, then a current will be induced in this loop. So a current will start flowing in this loop. With the help of the Fleming's right hand rule, I can find out the direction of the current which is induced in this particular wire, which is AB. So for this, you can see again I am using my 3 fingers, but now they are of the right hand. Again my forefinger is for the direction of the magnetic field. The middle finger, it will give me the direction of the current, and the thumb now will be pointing towards the direction in which I am moving the wire AB. So let us do this and find out. So here the thumb is pointing towards the direction of motion of the wire. My forefinger will point inwards and it is towards the magnetic field. So you can see that the direction of the current in this wire AB will be upward. So I will get this as the direction of the current and it will flow like this in the loop. Now this is governed by another equation which I can write it as F is equal to Q V cross B. So when you are moving this wire along this direction in the magnetic field, the charges in this wire will experience a force along this and they will start moving in this direction. That is what will create a current, and this is the induced current which we talk about. So you can see that we have the Fleming's left hand rule and the Fleming's right hand rule. But notice one thing. In this case, you have F is equal to I L cross B. This is a cross product of L and B. Similarly, here you have a cross product of V and B. So in both cases, we are dealing with cross products of vectors. But actually speaking, we do not need to remember this left hand and the right hand rule. There is a general rule for finding the direction of a cross product. So if you have, let's say, any two vectors, and these two vectors are, let's say, A and B, and you want to find out the direction of the cross product of A and B. So what do? We use a rule which is called the right hand thumb rule. For that, I use my right hand, and if I want to find out A cross B, I curl the fingers of my right hand and go from A to B. I go from A to B like this and see where my thumb is pointing. So here when I go from A to B, my thumb points inside the plane of the board. And this rule, I can use it for both the above situations which we have talked about. In this situation, you have I, L cross B. So I can find out the direction of the force by the right hand thumb rule. I go from, this is the vector L, and B is inside the plane of the board. So I go from L towards the B vector which is inside. So I curl my right hand and it goes like this. So you can see the thumb is pointing in this direction. And this is the direction of the force which we found out using the Fleming's left hand rule. Similarly, in this case, you have the cross product V cross B. So again I can use the right hand thumb rule, and if I go from here, the vector, this vector is V, it is in this direction and the magnetic field is inside. So I go from V towards the vector which is inside, which is the magnetic field, and I find that my thumb is pointing upward. So again I can find out that the direction of the induced current is along this direction, and I have used the right hand thumb rule for it. So for every cross product, we can use the right hand thumb rule to find out its direction. Thank you.